Hello students, welcome to Marine Engineering Tutorials. I'm Atul Kumar Gupta and I'm back with a new tutorial. We are currently studying marine boilers. Today we will begin our first lecture on marine boiler construction, and the topic for this session is smoke tube boilers. First we will discuss the construction and operation of Scotch boiler. Next, we will examine the internal details that support multiple furnaces in Scotch boilers. Then we will compare the advantages and disadvantages of corrugated furnace against plain furnace used in Scotch boilers. Next, we will study the arrangement of a Scotch boiler supplied as a packaged boiler. Then we will learn about the construction and operation of Cochran boiler of an older design. Next we will explore the Cochran boiler of the new design. Then we will learn the construction and operation of a spanner boiler. Finally, we will study the tube details of the spanner boiler. Let us now go through each of these topics one by one in the following slides. Scotch boilers. Smoke tube boilers are used for low pressure and low evaporation rate applications. They are commonly found on dry cargo ships where steam is required for heating and other miscellaneous purposes. Smoke tube boilers have a tank type construction, making them compact and easy to operate and maintain. Due to their limited use during the ship's port stay, they do not require frequent maintenance and major overhauls can often be deferred until their survey. This sketch shows a Scotch boiler with a single furnace, which was used on the earliest steamships and later on motor ships as an auxiliary boiler. It was eventually phased out due to the preference for vertical boilers. The boiler drum was formed by the main wrapper plating, usually in two parts, joined by double butt welding and attached to tube plates, which formed the main pressure parts. The front and rear tube plates were held together by main longitudinal stays to prevent buckling or distortion due to internal steam pressure. The boiler drum was mounted on its foundation with four anti-rolling stays. Two stays at the front end were fixed while the other two at the rear end were sliding to allow free thermal expansion of the boiler, thereby avoiding undue distortion. The furnace was of suspension bulb type, surrounded by water and occasionally corrugated for strength, which also provided increased heating surface area. A pressure jet burner was mounted on the front tube plate. The furnace was extended by a large combustion chamber made of thin plates supported by stays, girders, and tubes. Plain tubes and stay tubes in the ratio of 3 to 1 were fitted between the combustion chamber front plate and the front tube plate, as well as between the front and rear tube plates. These tubes first returned the flue gases to the front end plate and then to the rear end plate, from where they were discharged through the boiler uptake. The state tubes also supported the tube plates and the combustion chamber front plate. Two manhole openings were usually provided, one on the wrapper plating and the other at the bottom of the rear tube plate. These openings were compensated to restore plate strength, and the manhole on the wrapper plating had its minor axis parallel to the boiler axis. Two gauge glasses were mounted on the front tube plate with the bottom connection positioned at a minimum of 5 inches above the top of the combustion chamber. To prevent damage to the tubes due to shortage of water, the combustion chamber crown was fitted with a fusible plug. In modern boilers, this function is achieved by using a low water level trip device. Imported boiler mountings, as shown in the sketch, were installed at their respective locations. These included safety valves, steam stop valve, air vent, feed and check valve, and blowdown valves. Details of furnace and combustion chamber support. Smoke tube boilers are not suitable for high pressure applications because the furnace and combustion chamber are surrounded by water, which exerts significant pressure on their walls. When boiler is used for high evaporation rate, the furnace size must be large enough to generate the required volume of flue gases. However, increasing the furnace diameter requires greater wall thickness to withstand the higher stresses, which in turn reduces heat transfer efficiency. To overcome this limitation, a multi-furnace boiler, as shown in the figure, is designed to deliver high evaporation rate with improved efficiency. This sketch shows the internal details of a large capacity boiler used on earlier steamships featuring a triple furnace with two pass design. The weight of the furnaces and combustion chamber is primarily supported by longitudinal girders attached to the end covers. The combustion chambers are additionally secured by supporting stays connected between the combustion chamber and the wrapper plates. The boiler's cylindrical drum is fabricated from rolled wrapper plates joined by a longitudinal welded seam. Flat end plates are welded to the wrapper plates and are held together by main longitudinal stays to prevent distortion due to internal pressure. Two manholes are provided for internal inspection of the boiler drum, one on the wrapper plate and other on the front end plate. The boiler is mounted on its foundation with anti-rolling stays attached to the supporting saddle. This boiler, featuring a three-pass design, achieved steam pressure of up to 20 bar with an efficiency of 81%. It utilized approximately 5 square feet of heating surface per horsepower and offered a durable, low maintenance design. Other designs were also in use, incorporating 2 or 3 furnaces depending on boiler size and the required evaporation rate. Plain and corrugated furnaces. This sketch shows Scotch boilers with plain and corrugated furnaces. Various internal and external details are also illustrated. Let us compare the advantages and disadvantages of a corrugated furnace. Advantages of corrugated furnace. Corrugated furnace has following advantages. Higher strength against collapse. Corrugations increase resistance to external pressure and reduce the risk of furnace collapse under boiler pressure. Allows thermal expansion. Corrugations flex slightly to accommodate expansion and contraction of the furnace, thereby minimizing thermal stresses and the risk of cracking. Improved heat transfer. Corrugated furnace provide a larger heating surface area compared to plain furnaces, which improves heat transfer. The turbulence created by the corrugations further enhance the rate of heat transfer. Permits higher working pressure. The stronger construction of a corrugated furnace allows operation at high pressures compared to a plain furnace. Longer service life. Corrugations reduce stress concentration, thereby lowering the likelihood of fatigue failure over time. Better combustion efficiency. Turbulence created by corrugations improves the intermixing of air and fuel vapors, resulting in more complete combustion. Disadvantages of a corrugated furnace. Corrugated furnace has following disadvantages. Higher manufacturing cost. Fabrication of a corrugated furnace requires special machinery and skilled workmanship, which increases manufacturing cost. Difficult inspection and cleaning. Internal inspection of a corrugated furnace is more difficult, as soot and ash tend to accumulate in the grooves. Difficulty in repair. Repair of a corrugated furnace is more difficult than that of a plain furnace. Furnace replacement is often preferred over repair. Higher draft loss. Corrugations create additional resistance to flow of gases, resulting in higher draft losses. Not suitable for very high pressure. Although corrugated furnace allows higher working pressure compared to plain furnaces, they cannot match the pressure capabilities of water tube boilers. Package Scotch boiler. The sketch shows a packaged Scotch boiler with a single furnace and three parts design. 10 type boilers are usually supplied in package form with all associated equipment mounted on the boiler foundation. To relieve internal pressure, boiler is equipped with an improved high lift type safety valve with an easing gear arrangement. A steam stop valve is also mounted on top of the drum and can be accessed via a ladder. Water is supplied to the boiler by a feed pump mounted on the back plate. Earlier boilers were installed at the bottom platform below the load water line. Therefore, the boiler blowdown valve was a non-return valve to prevent the entry of seawater. In modern installations, boilers are located above the water line to prevent backflow. The blowdown valve is connected to an internal pipe to completely drain the boiler when required. The four draft fan supplies combustion air to the boiler through an air resistor. The burner assembly is fitted on the front plate and the exhaust gases leave the boiler from the opposite end after making three passes through the boiler. The control panel automatically maintains steam pressure, which can be monitored using the pressure gauge. This boiler was heavily constructed and had durable design. For ease of inspection and maintenance, the front and rear smoke doors were debited. It requires low maintenance and was usually operated at 10.5 bar with an efficiency of 81%. Cochran boiler. The Cochran boiler is a vertical multi-tubular smoke tube boiler developed by the Scottish company Cochran and Company in the early 20th century. Due to its simple construction, high efficiency, and compact design, it was widely used on ships where space is at a premium and a compact boiler is essential. The sketch shows a Cochran boiler of an older design with riveted construction. The boiler consists of a cylindrical shell with a dome-shaped steam space. A hemispherical furnace is attached to the boiler shell by an OG ring, whose enlarged view shows its minute details. As water circulation around the OG ring is poor, it is made of a thicker plate to provide a wastage allowance. Three telltale holes are provided to reveal leakage due to wastage of the OG ring. Handles are provided around the OG ring for inspection and cleaning. The bottom of the furnace is lined with fire bricks, which also encloses the burner assembly. Flue gases pass from the furnace to the combustion chamber, located at the back of the boiler through a throat. The top of the combustion chamber is supported by a gusset stay attached to the boiler shell. A large number of smoke tubes are attached to the tube plates, providing the required heating surface area for steam generation. All the smoke tubes are surrounded by water, and the minimum water level should be at least 6 inches above the crown of the combustion chamber. Flue gases from the combustion chamber make a single pass through the tubes and reach the smoke box, from where they are exhausted to the atmosphere. Access to the smoke tubes for maintenance and repair is provided by refractory line front and back covers. A manhole is provided in the steam space for entry into the boiler drum. Spheroid Cochran boiler. This sketch shows a modern Cochran boiler with a seamless spherical furnace and all welded construction. The boiler consists of a cylindrical shell with a hemispherical crown and a dished bottom which do not require stays. The spherical furnace is completely surrounded by water and does not require any furnace brickwork or refractory lining, apart from the burner quark. The spherical furnace provides a larger radiant heating surface and is therefore more efficient. The flue gases then pass into the combustion chamber attached to the outer shell. The hot gases make a single pass through the horizontal smoke tubes before being exhausted. These small bore tubes are fitted with retarders which improve heat transfer and by creating turbulent gas flow and also help keep the tubes clean. Access to the smoke tubes is provided by a refractory line back cover and an insulated front cover. Steam is separated above the water level and stored in the steam space. Access to the steam space is provided through a manhole. A number of handholds are provided at the bottom for internal cleaning of the boiler shell. The boiler is robust and easy to maintain. The working pressure range from 10.3 bar to 17.2 bar and the evaporation rate ranges from 991 kg per hour to 4550 kg per hour. Spanner boiler. This sketch shows a vertical smoke tube spanner boiler developed by the German engineer Fritz Spanner in the mid 20th century for industrial applications. It consists of an outer shell that encloses a cylindrical furnace which is connected by vertical smoke tube to a cylindrical smoke box at the top of the boiler. The bottom of the furnace is lined with refractory material. The vertical smoke tubes are of a special design known as swirly flow tubes which have a helical twist along most of their length and plain section at both ends. This design improves heat transfer by increasing the effective surface area and promoting turbulent gas flow. No stays are required for the outer shell. However, the flat tube plates are supported by plain stay tubes, which are expanded and then welded into the tube plates. Internal access is provided by means of a manhole. A number of handholds are provided in the outer shell for inspection and cleaning. Side holes of 6-inch diameter are provided at specific locations to facilitate inspection. All the tubes are surrounded by water up to normal water level. The burner assembly is attached to the furnace through the burner tube and fuel is burned in the water cooled furnace. Steam is separated from the water and collected in the steam space. The normal working pressure for this type of boiler is about 7 bar and the steam output ranges from 450 kg per hour to 2270 kg per hour depending on boiler dimensions. Drum and tube details. This sketch shows the drum and tube details of a spanner oil-fired boiler fitted with vertical smoke tubes. It consists of an outer shell 5 feet 6 inches in diameter, 3/8 inch thick and 10 feet 6 inch high, which encloses a cylindrical furnace 4 feet in diameter and 4 feet 4 inch high. The furnace is connected by the vertical smoke tube to a cylindrical smoke box at the top of the boiler, which is 3 feet 6 inch in diameter and 2 feet 5 inch high. The tube stack consists of 149 swirly flow tubes of 2 inch outside diameter, 10 standard wire gauge or 3.5 millimeter thick and 3 feet 9 inch long at triangular pitch of 2 and 708 inch. No stays are required for the outer shell. However, the flat tube plates are supported by 14 numbers 2 inch outside dia, 3/8 inch thick and 3 feet 9 inch long plain stay tubes, which are expanded and then welded into the tube plates. Internal access is provided by means of an elliptical manhole of size 16 inches by 12 inch. A number of handholds are provided in the outer shell for inspection and cleaning. In addition, 6-inch diameter sight holes are provided at specific locations to facilitate inspection. Fuel is burned in the water-cooled furnace by a pressure jet burner which is attached to 21.5-inch outside diameter burner tube. Only the bottom of the furnace is lined with reflective material and its inspection is facilitated through the burner tube. This completes our study of smoke tube boilers. This book has been written by me and covers all the topics as per Indian Maritime University syllabus. It explains key concepts using simple illustrations. The book also includes answers to all questions that have appeared in the examination conducted by Indian Maritime University. It will help students prepare effectively for exams and also support them in working safely with ships' boilers. I hope you enjoyed the lecture. Feel free to share your feedback in the comment section. If you found this tutorial helpful, consider sharing it with your friends. Subscribe to the channel to stay updated with upcoming tutorials. I'll be back soon with a new lecture. Thanks for watching till the end.